Hi, I'm Andrea, and this is AP Physics C Mechanics FRQs. Today we're going to be talking about 2019 Set 1 Question 2. So the question says, a pendulum of length L consists of block 1 of mass 3m attached to the end of a string. Block 1 is released from rest with the string horizontal as shown above. At the bottom of the swing, block 1 collides with block 2 of mass m, which is initially at rest at the edge of the table of height 2l. Block 1 never touches the table. As a result of the collision, block 2 is launched horizontally from the table, landing on the floor at a distance of 4l from the base of the table. After the collision, block 1 continues forward and swings up. At its highest point, the string makes an angle theta max to the vertical. Air resistance and friction are negligible, and all algebraic answers in the terms of m, l, and physical constants as appropriate. Okay, this is a very complex situation. So we have a pendulum swinging, and that makes me think of conservation of energy. We have blocks colliding, which makes me think of conservation of momentum, and we have blocks flying off the table with an initial horizontal velocity, which makes me think of kinematics. So that's what I think the overall concepts will revolve around. So let's look at part A. Determine the speed of block 1 at the bottom of his swing just before it makes contact with block 2. Okay, so looking back at the overall concepts that I just talked about, I immediately think, oh, conservation of energy could apply to this. So that's the path I'm gonna follow. So whenever I get to a conservation of energy problem, I like to explicitly write out conservation of energy, this concept, just to make sure that the grader knows that I am using this concept. So conservation of energy says that energy initially equals energy final. So we can break down the energy components into initial potential plus initial kinetic equals to final potential plus final kinetic. So we know that initially the block 1 is at rest, so there's no kinetic energy initially. To make the problem easier, we're going to set 0 at where it's table level so that we can avoid having potential energy in the final position. So we're going to make an initial position where the block is released from rest, and we're going to make the final position right before the block hits block 2. So initially the potential energy is mg height. We set 0 at table level, and we know that string is length L, so that we know that block 1 starts at a height of L. So that is our initial height. And for final kinetic energy, we can just use the regular kinetic energy equation, 1/2 mv final squared. So then the mass of block 1 cancels out, and we can move the 1/2 to the left to get 2gl equals vf squared. So then we can take the root of both sides, and we get vf equals root 2gl. And that is your answer for part 1. Alright, for part B. On the dot below, which represents block 1, draw and label the forces, not components, that act on block 1 just before it makes contact with block 2. Each force must be represented by a distinct arrow starting on and pointing away from the dot. Forces with greater magnitude should be represented by longer vectors. Okay, so this question literally asks for a force diagram of block 1. So block 1 has two forces acting upon it. The first one is force due to gravity, or otherwise known as weight, and the other one is the string's tension. Since we know that the block is swinging in a circular motion, we know that the net force should be equal to the centripetal force. So we know that the block's net acceleration or net force should be towards the center at which the block is rotating about. So the center at which the block is rotating about is where the string is held, right here. So when block 1 is in the position just before it hits block 2, it is directly underneath the center of the rotation. Since we know there's only two forces acting upon the block, gravity going towards the table or towards the ground, tension going perpendicular with the table surface, and that the net force is going upwards, we know that tension force is greater than the gravitational force. So we have to draw the tension force and label it longer than the gravitational force, which we can just label Fg or W. And that's your answer for part B. Okay, part C. Derive an expression for the tension Ft in the string when the string is vertical just before block 1 makes contact with block 2. Draw anything other than you've shown in part B to assist your solution. Use the space below. Do not add anything in the figure of part B. Yes, do not edit your answer once you've written it unless you've noticed that it's wrong. So for part C, first thing to notice is it says derive, which means you have to use an existing equation either from the other parts of question 2 or from the equation sheet you get. So since it's derived an expression for a force, I like to use Newton's second law. So we know that F net equals mass times acceleration, or net acceleration. And since we know that the block was moving in a circular motion, we know that the net force is equal to the centripetal force, which equals the mass times velocity squared over r, or radius. So we also know the net force has two components, gravity and tension. So it also equals to the tension force minus the gravitational force. So we know that the gravitational force of block 1 is mass times gravity. So we can rewrite this equation to mass times velocity squared over r equals to the tension force minus mass times gravity. For velocity, we can use our answer from part A. To recap, our answer for part A is velocity equals root 2gl when block 1 is just going to make contact with block 2. And this is the exact point at which we want to find ft. So r is the radius from the object to its center of rotation. And we know that the center of rotation is where the string is being held. And as you can see, the r is the length of the string, which is just L. So we can substitute L in for r. By substituting both of these values in, we can get mass times velocity squared. You can get rid of the square root, equals 2gl over L equals ft minus mg. So obviously the L's cancel out, add mg to both sides, so you get 2gm plus mg equals ft. And you can add these two together to get ft equals 3mg. But this m is the mass of block 1. So we have to substitute 3m in for m. So ft actually equals to 9 capital mg. And that will be your answer for part C. Now for parts D to G, the value of the length of the pendulum is L equals 75 centimeters. So this is extra information. They're actually giving you numerical values, but they didn't give you in standard SI units. So I like to immediately convert everything I get into SI units. So 75 centimeters is equal to 0.75 meters. So part D asks you to calculate the time between the instant block 2 leaves the table and the instant it first contacts the floor. Alright, so we know that block 2 leaves the table with an initial horizontal velocity, but we haven't found velocity yet. But we do know other information to help us with this problem. My mind immediately thinks of the kinematic equations as we've talked about before in the overall concepts. So even though we don't have this initial horizontal velocity, we can use other components to help us figure out this problem. So looking at the y component of the block flying off the table, we know that the displacement it travels is the height of the table, which is 2L. We also know that the acceleration it feels is g, which is from gravity, because the only force exerted on the block is the force due to gravity. And we know that we're trying to find time t, and we know that the initial vertical velocity is 0. So using the kinematic equation, displacement equals to initial velocity times t plus 1/2 at squared. You can plug in all these values into the equation. So for d we have 2L equals initial velocity is 0, so this will be 0 plus 1/2 a is g, and then t is just t squared. So if you divide 1/2 g on both sides, you get 4L over g equals t squared. So then you know that t equals root 4L over g. And we actually know the numerical value for each variable in this equation. So we can actually plug in the numbers 0.75 for L and 9.8 for g, or 10 for g. But I like to use 9.8. If we plug all this into the calculator, you get t is approximately 0.55 seconds. But we're just going to write this as t equals 0.55 seconds. And that's your answer for part D. So part E asks to calculate the speed of block 2 as it leaves the table. So in the very previous part, we were asked to use kinematics. So I'd like to use kinematics again. So calculate the speed of block 2 as it leaves the table. We know that block 2 leaves with a horizontal speed, a pure horizontal speed. So we can use the t equals 0.55 seconds. And we know that the horizontal displacement the block travels is 4L. So we can write displacement equals 4L. And there's no horizontal acceleration since air resistance is negligible. So we can write A equals 0, and we're trying to find the initial velocity of the block. So using the kinematic equation, D equals VOT plus 1/2 t squared, we can find the initial velocity. So we know that distance is 4L. We know that VO is what we're trying to find. We know that t is 0.55. And we know that a is 0, so this whole component part will equal 0, so it's plus 0. So we divide 0.55 to the left and plug in 0.75 for L. Plugging all that into the calculator, you get V initial equals 5.45 meters per second. And that's your answer for part E. Part F wants us to calculate the speed of block 1 just after it collides with block 2. So because we're talking about collisions, we're definitely going to use conservation of momentum. And like the conservation of energy in part A, I like to explicitly write conservation of momentum so that the grader knows exactly which concept I am using. So the conservation momentum equation says that the momentum right before the collision equals the momentum right after the collision. So right before the collision, we know that block 2 is at rest and block 1 is moving with the velocity that we found in part A. And since we know momentum is mass times velocity, we can just write the mass of block 1 times its initial velocity plus 0 equals the initial momentum. At the final momentum, both block 1 and block 2 are moving, but they are moving at different speeds. So we know that block 1 is moving at its own speed and block 2 is moving at another speed. So actually we found this other speed from part E. So we know that the final velocity of 2 equals to 5.45 meters per second. And we know that the initial velocity of block 1 is equal to root 2gl, which we can just plug in values that we've gotten for parts D through G. And we know the mass of block 1 is 3m, and we know the mass of block 2 is m. So besides Vf, which we're trying to find, we know every other value. So we can just plug in the values, cancel out, move things around, and find Vf. So plugging in things, it's m1 is 3m times its initial velocity, which is root 2gl, equals to m1 is 3m times its final velocity plus m2, which is m times its final velocity. Both sides we can cancel out m, so we get 3 root 2gl is equal to 3v final plus 5.45. We can move the 5.45 to the left and then divide everything by 3. So we get 3 times root 2gl minus 5.45 all over 3 equals the final velocity that we're looking for. So now we can plug everything into our calculators to find out that Vf equals to 2.02. So this is your answer for part F. Part G, calculate the angle theta max that the string makes with the vertical, as shown in the original figure, when block 1 is at its highest point after the collision. So obviously block 1 is moving at a different velocity before the collision, so its maximum height is going to change because some energy is lost during the collision and transferred from block 1 to block 2. But we can use the conservation of energy concept with block 1's new velocity. So again, I like to explicitly write conservation of energy just so the grader has an easier time figuring out which way I'm doing things. So this time we're going to pick an initial point is block 1 right after the collision, and the final point is block 1 at its maximum angle at theta max. So again, its initial energy equals to the final energy. So we're still going to make our zero height at the tabletop so that it's easier for us to calculate stuff. So block 1 initially doesn't have any potential energy, but it does have kinetic energy. And when block 1 is in its final position at theta max, it does have potential energy, but it does not have kinetic energy. So we can just write the initial kinetic energy equals to the final potential energy because initial potential is 0 and final kinetic is 0. So kinetic is 1/2 mass of the block times V initial squared. And the final potential energy is mass times gravity times its height. So for the initial velocity, we actually know this because we just calculated it from part. So we know that the initial velocity is equal to 2.02 meters per second, but we need to find what h is and how it relates to angle max. Good thing is that we know the length of the string is L, and we know that the block travels a certain height of h. And we know that the angle the string makes with its vertical is theta max. So if we pull this triangle out, actually, if you'd like to draw this, we get a triangle with a hypotenuse of L with one side of its h and an angle of theta max inside. So the relationship of theta to h actually is cosine theta max equals to h over L. So we can move L to the other side to get L times cosine theta max equals to h. So we can substitute that in. We know what L is and we can find theta max. So also another point, we can cancel out the mass from both sides. So we get 1/2 V initial squared equals to GH. So we can substitute things in here to get 1/2 2.02 squared is equal to G times L cosine theta max. It's a bit cramped here, but on the actual test, it's best to write line by line and line up your equal signs. So we can divide both sides by GL and get 2.02 squared over 2GL equals to cosine theta max. Then we take inverse cosine of both sides to get theta max equals to inverse cosine 2.02 squared over 2GL. And if we plug all of this into a calculator, and I like to use 9.8 for G, we can get theta max is equal to 43.5 degrees. Make sure your calculator is on degrees and not radians, because AP Physics C Mechanics needs to have answers for angles in degrees. And that's your answer for part G. If you're still a bit confused about how in the world did I know, oh, this question you need to use conservation of momentum, oh, this question you should use conservation of energy. So there's a link in the description where I've categorized each question overall and their component parts into groups of big concepts that I've noticed and I like to remember. And for each concept, there's a link to how in the world can you identify this question wants to test this concept. I hope I've helped you clarify how to solve this problem, and I'll see you in the next explanation video. Bye!